students. In the last class we have discussed about the theory of pure torsion. Today we will solve the moment resistance. We will find the moment resistance of a solid shaft. At the last class we have discussed that what is the relation between tau, that is the maximum shear stress at the outmost surface of a shaft, and the radius of a shaft with the modulus of rigidity, and the theta, that means angle of twist, and the length of the shaft. Now let us find out what will be the moment resistance of a particular shaft. Suppose we are taking a shaft whose radius is r. This is the cross section of the shaft, right? This radius is r. Now suppose we are considering one part or one element which is situated x distance from the center and has a thickness of dx. So x distance apart from the center and the thickness of this element is dx. Now if you consider this element, you will see that suppose the shear stress at this particular element is tau x, as because we know that for particular distance, for particular radius, our shear stress will be different. So suppose we are considering at x distance, our shear stress is tau x. So those shear stresses will act like in these directions, and due to this shear stresses, the resistance due to the twist will be generated, right? Now suppose let us find out what will be the shear resistance offered by this particular element. If we consider this element only, what will be the shear resistance if this is shear stress, and then what will be the shear resistance? Shear resistance will be the shear stress multiplied by the area, right? So shear resistance for this particular element, resistance for this particular element offered by the element will be equals to tau x, that is the shear stress, multiplied by dA, and dA is the area we are taking, the elemental area, right? Now from the last class we have seen that tau x divided by x, that means the shear stress in a particular point which is situated x distance apart from the center, will be linear. That means this will be equals to tau, which is the maximum shear stress at the end, that means at a point which is r distance apart. So this will be equals to tau by r, right? So we can replace this tau x, and we can write x by r tau into dA, right? So this is the shear resistance offered. Then what will be the moment resistance? Moment resistance offered by the element will be equals to this shear resistance multiplied by the distance, that will be the moment resistance, force multiplied by the distance. So all the force, if you will, it will produce some moment with respect to the center, which will be equals to the force multiplied by the distance. force multiplied by the distance. So this distance will be x all through, so this will be equals to this shear stresses multiplied by the area, you will be getting the force, multiplied by the distance, you will be getting the moment resistance, right? So this is the elemental say moment resistance. So what will be the total moment resistance offered by this solid shaft, right? So the total moment resistant, we can say the total moment resistance offered by the cross section, this will be equals to, suppose we are denoting with this TR, the torsion resistance. So this will be equals to summation or integration from 0 to r, right? If you vary this value from 0 to r, you will be getting the total value. So this we can say tau by r summation of dA into x square, right? But this part is basically represent the moment of inertia, right? What kind of moment of inertia? The moment of inertia of the section of the shaft about the axis, right? About the axis means this, right? So the moment of inertia about this axis of the shaft, right? So this we can uh, replace with the value of j, where j is equals to the moment of inertia about the axis, right? This type of moment of inertia, we can call it the polar moment of inertia, right? So if you replace, you will be getting the value tr equals to tau by r into j, right? Now obviously the applied load and the resistance will be equal, right? Will be same. If this section is in equilibrium, if this section has not failed yet, then the resistance will be equals to the applied load. So the tau t total torque. So the resistance is equals to this, equals to this, right? Now from this we can write that T by J is equals to tau by R, right? This is one relation. Now at the last class we have discussed this tau R is basically nothing but c theta by L, where c is the modulus of rigidity, theta is the angle of twist, and L is the length of the shaft, right? Remember that, right? So this was the relation. So we can say this T by J is equals to also equals to this, right? And eventually we have written that this is equals to again the tau x by x, where tau x is the shear resistance, shear stress at a particular point x distance apart. So we can say this is also equals to tau x by x, right? Now let us find out what will be the value of moment of polar moment of inertia and polar modulus, right? So let us find out the polar modulus. Now we have one equation, that is tr by j equals to tau by r, right? we are getting from this equation, we are getting this, right? So from this we can say Tr is equals to tau multiplied by J by R. Now this is the polar modulus, right? G by R, we can say this is polar modulus, and we can represent this with ZV. Suppose we are indicating this with ZV, this will be equals to J by R. So this is equals to stress multiplied by ZV. Actually ZV we generally use for plastic modulus, so we are not using this, so we are using ZV. So Tr is equals to ZV. We know the stress multiplied by the modulus is equals to will always be equals to the moment. So in this case moment moment is equals to stress multiplied by this ratio, which is actually nothing but the modulus, one kind of modulus, and this is called the polar modulus. Hence we can say that for a shaft of a given material, the magnitude of the polar modulus is measure of its strength in its resisting torsion, right? So polar modulus is nothing but the strength against the torsion, right? So let us find out what will be the value of this J, the moment of inertia about this axis, that is polar moment of inertia and polar modulus. What will be those values? We have taken one element, right? In this circular shaft we have taken one particular element, this element, right? This is x distance apart, thickness of dx, right? Now what will be this area of this element? Area will be equals to, for a hollow circular section, the area is pi multiplied by r square minus capital R square minus small r square. So suppose we are taking x square minus sorry this if we are taking, we can take this also, but if we are taking this as the higher one, so we have to write pi x plus dx square minus x square, whatever the result will be same. So this one is out, suppose. So if this is our area, we can write this as pi x square plus 2x dx plus dx square minus x square, right? So x square will be omitted, and this part, as because dx is pretty small, we have considered this small thickness, so dx square will be small, pretty much small, right? So this is square term, so we can neglect this part, as because this will be pretty high, pretty small. So this will, we can say this will be equals to 2 pi x dx, right? We can write this. Now what is J? Last class we have not it done at the last part we have found that this J is equals to nothing but J is equals to the summation, if you sum up this from 0 to R of dA multiplied by x square, then you will be getting J. So this we can write this will be dA will be equals to 2 pi x dx multiplied by x square, right? So basically this is constant, so 2 pi we can take it outside. This will be equals to x cube dx. This value will be, after integrating, we can get 2 pi x to the power by x to the power 4 by 4. This value will be from 0 to r. So if we consider this r value, 0 will be 0. If we consider this r value, we will be getting 2 pi r to the power 4 by 4, right? This is the value of j. Now if you denote this in terms of diameter, not in radius but in diameter, we will be getting 2 pi d to the power 4 by 4 to the power 4 multiplied by 4. so so this will be equals to 4 multiplied by this is 4 4 multiplied by r. This will r will be equals to d by 2, so d to the power 4 divided by 2 to the power 4, that is 16. So if you cut this, you will be getting pi d to the power 4 by 32. This is the value of j, right? This is the value of j, the polar moment of inertia, right? Now what will be the value of the polar modulus, right? The polar modulus ZV is equals to nothing but J by R, right? So J by R means, what is the value of J? The value of J we have just pi d to the power 4 pi d to the power 4 divided by 32, and this R is nothing but d by 2, so this is d by 2. Then we will be getting pi d cube by 16, right? So ZV is equals to pi d cube by 16. So this is the value of the modulus, the polar modulus of a solid shaft, right? Then what will be the moment of resistance of a solid shaft? This will be equals to tau into ZV, which is equals to tau multiplied by d cube by 16, right? This is the moment of resistance of a solid shaft, okay? So this is our class for now. Thank you.